I want to thank our hosts for having us here. I want to thank you, Tim, for that fun lightning talk. And thank you all for having me come and speak again at the Munich User Group, which, as Klaus pointed out, is something you should be very proud of being part of. It's really exciting to be here. This talk that we're going to do tonight, I did last week at Meeting C++. And as I was talking to people there, someone pointed out to me that they didn't know that I did training. And I said, well, that's really important for me to tell people because I need the business, right? And so here's my ad, and I'm going to ask you this to put up your hands if you think your life would be better if you knew more C++. All right. Now here's the real question. That's not even the real question. The real question is this. How many of you think your life would be better if your coworkers knew C++? All right. So send me an email and we can make that happen. All right. So tonight's talk I'm calling Modern Template Techniques, but the way I think of this is actually it's templates 201. It's not 101. We're not going to talk about beginning syntax of how to create a template. What we're going to do is we're going to talk about the techniques that you use after you get past that and before you start getting into template metaprogramming. So we'll talk a little bit about template metaprogramming. And we will, in fact, kind of as a review, take a look at we're going to write our own function template. How many of you have written a function template from scratch before? All right, well, most of you have. So those of you who haven't, you're going to be able to update your LinkedIn profile to say that you've now written. So we're going to write this function template from scratch, and it's just the simplest thing. We're going to call it add. It's just going to add two things. That's all it's going to do. But you're going to write it, not me. So how do we start a template? What do we need here? All right, template, and then we're going to need the type we're going to add. So 2 ints. Well, we could have it. If it's a template, we don't know what the types are. So we're going to say it's what? Just T. OK. Well, we're going to add two things of the same type. Let's start with that. So here is template class T. OK, now we need to have the signature of our function, which I told you the name of it. But what do we want to return? T. We probably want to return T, and then we're going to add T, maybe an A and a B. OK? Now's the hard part. Now we have to implement it. So what's the implementation going to be? What? Return it. You know, that might not be as hard as I thought it was going to be. OK, but there is a problem here. This isn't quite ready to ship because this unknown type might be expensive. So what do we really want to do? Right. We want to take this by reference rather than by value because we don't need to take a copy in order to add two things, right? We just need to be able to read it. So we can do it like this. OK? All right. We've done it. We have implemented our template. And because we've updated it to take it by reference, we're ready to go. It's going to make one little tiny change before we move on. I would like it to add things of different types, right? Not just the same type. So what are we going to need to do? We're going to need to add a new template parameter. By convention, we usually do after T, we do U. OK. So that's all we need to do. We need to add a new template parameter, and we have class T and class U. And now we can add these two things together, right? OK, we good with this? All right, let's not get ahead of ourselves here. All right, so what's the problem with this? OK, the return type, right, which I've assumed is T, but it could be U, right? But it has to be either T or U, right? No, there's no particular reason to believe that because we're adding two types, the answer has to be either of those two types. In fact, if we look at adding a char and a short, the standard says this is going to return an int. So it's possible that adding T and a U might return yet some other type. So let's set aside the template syntax right now and just tell me in words what is it that we want to return? What's the type we want to return? Yes, yes. It's whatever the type is that you get when you add together these two types, the T and the U. So what we want to do is that, and how do we say that? What is the operator we can use to say what a type is? What? Well, auto would give us a value as well as the type. I want to get just what the type is. Decal type, that's right, decal type. So here we go. We now say that what we're returning is the decal type of adding T and U. Okay, this is good? No except. we don't know for certain it is no except, so we don't want to declare it as no except. It's more complicated than that. What's the problem with this? What? It doesn't compile because decal type doesn't take types. Decal type has to take an expression. So we don't want T and U. What do we want? We want A and B. Okay. All right. So there we say decal type A and B. Okay. Now is that good? What's wrong? A and B are defined. I define them right after I use them. Isn't that what the compiler wants? What? All right. So what is it we really need to do here? We need to use the trailing return type, right? Right? Okay. The reason I went through all this is because I want to make the point that in order to write the simplest template function in the world, maybe it's not quite the simplest, but in order to do that, we need not one but two features from C++11. We needed decal type, which was introduced in C++11, and we needed trailing return type syntax, which was introduced in C++11. We need both of those in order to do this very simple template. Now, that's letting us know that we're seeing a lot of progress because a lot of interesting templates were written for classic C++, but we can do a lot better now. In fact, this is C++11. We can do something even better in C++14. We can take advantage of type deduction for the return types. So in C++14, it will look like this, and that's even easier to write. And in fact, that makes templates a lot easier. We don't even have to specify what the return type is. We can let the compiler figure it out for us. Any function where we're giving the compiler the body, the compiler can look at that body and say, oh, I know what the return type is. You don't have to say what it is. And that makes working with templates an awful lot easier to do. Okay. So now I'm going to talk a little bit about CRTP, or the static polymorphism. So what is polymorphism? There's a number of different ways to look at it, but the way I want to focus on it right tonight is to say that we have some kind of common interface, but the implementations differ by different classes. So in an object-oriented world, dynamic polymorphism, we would have a base class which defines an API with virtual functions, and we dispatch to that at runtime. But static polymorphism relies on this curiously recurring template pattern, and that name comes from the fact that this pattern comes up again and again, but not necessarily within C++, although it does. The name actually came in an original article was talking about looking at other languages and saying this pattern actually comes up in other languages that do this sort of thing. So that's where the name actually refers to. But what we're going to do is we are going to take advantage of the fact that the compiler knows the actual type at compile time. Not when we wrote the code, because we wrote the code without making assumptions about what the type is going to be. But we write the code, and the compiler is going to take advantage of that at compile time. So here's how this works. Here is the curiously recurring template pattern. We have a class that is derived from some base template, where the template is templated on the type that's doing the deriving. Now, when you first look at that, you might say, wait a minute, does that even compile? It looks as if what you're saying is, well, this is derived from something that has to know what the type is that it's deriving from. And in fact, no, this actually works, and it works really well. So here's what we're going to try to do. We want to create a base class that defines an interface for how we can call something, but we want the derived classes to implement that. And we want to do this without virtual functions. And we want it to be type safe. So here's how we're going to do it. Here is our base class, and it defines an interface, which in this case is real simple because we're not passing anything to it. But inside this interface class, what we're going to do is we are going to do whatever kind of precondition verification we want to do, and then we're going to call the implementation. But remember, the implementation isn't anywhere in our interface. It's in the derived classes interface. So we have to cast ourselves to be the derived class object, which we know works because the point of this template is that it's templated on whatever the derived type is. That's what the curiously recurring template pattern is for. And then we can do whatever post-condition verification. So the way we would then implement this is an implementation implements from the base class, templated on its own type, and then we can put anything we want in the implementation. So then we just create a derived object we call interface. We call against the base class type, but the implementation is actually in the derived class. Okay? And that is the curiously recurring template pattern specified. Here is what Steve Dewhurst considers the traditional first example. So what we have here is a base class that keeps account of all the objects of this type in existence. Okay? Notice there's a private inline static long that is my counter. And because we're taking advantage of this from C++ 17, we don't actually have to provide a definition for this. The compiler is just going to provide this for us. And now what we can do is we can derive, I have my string derives from counter of my string. And that's all I have to do. Go ahead and implement my string however I want it. But anytime I would like, I can call my string. Now this is a static member function to get count. So I don't use, well, I could use the arrow syntax, but essentially I'm saying my string : get count, and it tells me how many objects of this type there are. And there's no virtual functions in here. This is done entirely, the dispatching is done entirely at compile time. Okay? All right. And it does give us this answer. Okay. So here's another very simple example. And in this example, what we'd like is to be able to make a clone of a particular type. So our base class has a function call called clone. And what we do is we do a new of the derived type, not the base type, of the derived type. And the reason this works is because we're templated on the derived type. We know what the derived type is. So when we do our when we derive from this, we derive from clonable. We don't need to do anything at all in the derived class. We just derive from clonable. But at any point, we can call on the derived class and say, call clone, and it does, in fact, return a clone, which is a clone of the original. Okay? Just another example of what we can do. So here's a little bit more interesting example. This is from Barton and Nachman, but had shared with me from Steve Dewhurst. So here is a base class called EQ, or equal class, and what it does is, given a comparison operator, it implements for us the equality and inequality operators, or not equal operators. And so this is done in the base class for us. So when the compare is defined in the derived class, it will return a negative value for less, 0 for equals, and positive value for greater. This comparator is the syntax of string compare. It's very common. So now we've also created a relation class, which will tell us if something's less than equal, greater than, or greater than equal, again, all using the compare. So we're putting all this logic in the base class, and then we can create a class like, for example, the complex class. Now, complex won't support less than or equal because complex doesn't do that. But it will do equality and inequality. So you want to derive your complex class from eq of my complex. But for a string class, you want to be able to do all of these relations, equal, not equal, less than, all these relations. So you derive my string from eq of my string and rel of my string. And it gets all of these operations from it. Okay? I'm going to do one last example here. This is kind of a real-world example that we see in the standard library now, and that is that if we have an application, and in our application, all of our widgets are kept in shared pointers, right? So the widgets are kept in a shared pointer. And then one of the functions that we have on the widget is we can say this widget has been processed. Now what we want to be able to do is we want to keep a collection of processed widgets. So you see that vector of shared pointer. That is, all of the processed widgets are going to be, or a pointer to them, will be found in the vector of processed widgets. So once we process a widget, we do whatever it is that we want to do the processing, right here, and then we want to add it to the processed widgets vector. And that's where we're calling in place back of this. But in place back of this is an uh-oh situation. What does uh-oh mean? What's the problem here? Right, this is not a shared pointer, but it will compile. Why? Because in place back, unlike pushback, doesn't expect a shared pointer. What does it expect? A constructor argument to make a shared pointer. So this is, what is its type? Pointer to widget. So if I pass this into in place back, can I convert a pointer to widget into a shared pointer? This compiles. But it's a problem. Why is it a problem? What's the problem here? Right. We started out by saying that in our world here, all widgets are kept in shared pointers. So this widget is already owned by one shared pointer. We've just created a new shared pointer that's also thinks it owns this. Now, the whole nature of shared pointers is you can have multiple shared pointers to an object. That's safe, as long as the way you get there is by copying a shared pointer, not by creating a new shared pointer, which is what we just did. So this is the problem. So how do we get around this problem? The way we get around this problem is to derive widget from enable shared from this of widget. So what is this? What this is a base class that's designed to be a CRTP base class. In other words, you derive from it and instantiate it on whatever the type is doing the deriving. And what happens internally is that this base class has a weak pointer to whatever the type is, but the base class, in order to have a weak pointer of the type, needs to know what the type is. So that's why we have to tell it, by the way, I'm going to derive from you with a widget, so the base class has to know it's instantiated on widget. Okay? So this is a practical application of the CRTP that's already in the standard library. All right, so this is basically showing you how to do this. Now, there's a typo in this code. Who sees the typo? There's a bug in this code. What's the problem? Okay, so in the first case, we have derived 1, which is deriving from the CRTP base, instantiated on derived 1. That's fine. But the second example has derived 2, which is instantiated on CRTP base of derived 1. Should be derived 2. And this base is probably going to cast itself to derived 2. And it's going to do that statically, meaning there's no runtime checking of that. So this typo is going to be a real problem, right? Does everybody see how this is going to lead to undefined behavior? Because we have an object of derived 2 that's going to cast itself to be a derived 1. That's going to be a problem. How can we fix this? What can we do? Well, we can fix the typo, right? Well, that fixes it. But how can we prevent this from happening? Well, what we can do here is we can say that we want to have the base class, the constructor of the base class, we will make that private, which means the only way we can construct this object is if we're doing it from either a member or a friend. And then we will declare the derived class to be our friend. So given this, if we want to instantiate struct CRTP base on derived 1, then we can only create that as a base for a derived 1. You see the problem? You see the solution? See why this works? Okay. It's just a nice little trick to prevent us from having bad inheritance. Okay? So it's based on the fact that a private constructor can only be called by a class that is a friend of whatever the base class is. That's how it works. All right. So now we're going to start to get into the basis of metaprogramming with type traits. And what type traits are attributes of types that we can query at compile time to make possible decisions about how we want to implement things. All right, so how can we determine if a template type is an int? Well, what we're going to do is we're going to create a type to do this. And the type we want to create is going to be called isInt. And since most types are not ints, we're going to say that it has a member that is the value of this isInt. The value is false. And we've said that this value is a static Bool const, and we need to be able to do that because we have to be able to query this at compile time. So if it was not static Bool const, we couldn't query it at compile time. So now we need to do the situation, well, what if t really is an int? Well, the way we handle that is by specializing this. So now we're going to specialize this for the case where it is an int, and you see that in that specialization, in that situation, we will set the value to be true instead of false. Okay? And then that allows us to do something like this, where we're going to say isInt of float and write it out in isInt of int, and of course, float is false and int is true. And I say, well, that's pretty straightforward. Why are we going to all this trouble? You've got it right there. You know, isInt of float. Of course, you expect that to be false. But the idea here is that it would be more complicated. It's isInt of t or isInt of u. That's what we're trying to be able to figure out. Okay? All right. So let's make one more. Well, I should say, as of C++ 17, we have this convention because we can do templated aliases. We're going to say that isInt underbar v is the templated of : value of isInt t : value. This is this just makes it so that we don't have to write as we did. In this previous example, we actually had to write isInt of float : value. Now we'll just say isInt underbar v of float, and we don't have to write the : value. Get rid of that. All right. So next step, we want to see if two types are the same. Are they the same type? Well, again, we're going to do this something very simple. We're going to say is same, and the default is going to be false. But we're going to specialize it for the situation where the two types are, in fact, both t, for whatever t is. And for that situation, we'll say that's true. And again, we need to make is same underbar v. We need to define that as just the is same : value. Okay, so it makes it a nice step. So we can do something like this then. We say is same v float in int, is same int and int, and we don't have to say : value because we've done the underbar v. Okay. All right. So now we want to start talking about type functions. We were talking about type traits. And type traits are values. They are attributes of types that we can query at compile time. But now we want to talk about type functions. And what's a type function? Well, a type function is a function that you pass one or more types to as parameters, and what you get back is a type. So before we were getting values back, now we want to get types back. Now, type functions are not supported in C++ as first-class citizens. C++ doesn't have type functions. But we can emulate these very easily with the same kind of technique that we did with the : value. We can create a template that has the answer, or the return type, is actually going to be : type. Okay? All right. So, and then we were also going to define a type function underbar t, so we don't have to say : type all the time. All right. So here's an example. Here's a type function. I want to be able to remove a const. So whatever type I give it, I want to have the exact same type, but with const removed. And so the straightforward thing to do is to say, well, if it's not a const, then it's pretty simple. I'm going to declare type to be an alias, a type alias, and say it's the alias of t. But if it is const, then I can create a specialization for the situation where it's t const. And in that specialization, I'm actually saying the same thing. I'm saying using type t, but the difference is it's different t for the specialization because pattern matching has pulled the const out. So both of these are going to return a value that doesn't have const. And then, of course, we want to do the remove const underbar t, which defines our type for us. And then we can do things like this. We can say is same v of int and remove const of int const, or is same v of int const and remove const. And so we get true in the first case and false in the second case. You see how this builds up? All right. I mean, we could go through all this all night and do different things, but you get the pattern. You understand what we're doing. And in fact, these type traits, which you, of course, find at CPP reference, right? All these type traits are defined in the standard for us. There's all sorts of things you can ask. And you can see, I mean, I understand you probably can't read those because it's pretty small to get them all to fit, but you get the ideas. You can get information like, you know, is this a member pointer? Is this a union? Is it trivially copyable? Or all these kinds of things that we can get. Remember, none of these are runtime. This is all something to do with the type itself. So we can make these decisions and make decisions and write different code depending on the compile time properties. Now, there's one particular one we're going to dive into, and that's this under the miscellaneous, and that's enable if. So we'll get to that. We'll come back to that in just a bit. So these type traits and type functions are the basis of metaprogramming. And now we're going to talk about being able to do different things at compile time based on this kind of decision making. So first thing we're going to talk about is tag dispatch. And the way this works is, let's say we have in the standard, we have something called STD distance. STD distance takes two iterators, takes a pair of iterators, and it tells us how far we have to go to get from one iterator position to the other iterator position. What's the distance in terms of essentially increments? Okay, does that make sense? Everybody know what we're trying to do? So what would be the order of that operation? Depends on the iterator, right? If you have a random access iterator, what would be the performance of this? It's constant time, right? But if you don't have random access, how are we going to calculate this? You're going to have to, yes, it's going to be linear, right? So what we would like to do is, we of course want to get a correct answer in every situation, but what we like to do is use the algorithm that's going to give us the best performance as well. So we really have two different functions here. So one function, the top one here, just uses iterators with no assumption about what they are, and so it goes into a loop and it counts the iterations until they become equal, right? They keep adding the first until it becomes equal to the end and adds one. Everybody see that? And again, the order is linear order. All right, but if we have a random access iterator, then we can do it with a constant time operation. Does everybody see this now? Okay, now the problem though is that we somehow have to know which of these two to call. So how do we do that? Or as I'm saying here, what's wrong with this? Well, what's wrong with this is that despite the fact that I've given these different names, I called one iterator and one RA iter, but from the compiler's point of view, that name doesn't actually mean anything. So what the compiler is actually saying here is, you've just redefined this. You just wrote it two different ways. And that's great. I have two different functions. Call this one in the right case and call this one in the right case, case closed. Problem is the compiler doesn't see it that way. The compiler says, well, which is the right case? So the way we're going to do this is we're actually going to make the signatures different by adding a tag at the end. Now what's a tag? A tag is a parameter that you're not actually going to pass a value to. But you have to, you're not going to use the value, I should say, but you have to pass something because the compiler is going to use the type of the tag to figure out which of the two functions to call. So the function signatures up till now are exactly the same. Now we want to add two different types. So we call with one type, we get one function, and with the other type, we get the other. So what we do is these are actually defined for us in the standard. There is something called an input iterator tag and a random access iterator tag. These tags come from the iterator traits. And so the idea is now I have two functions. And if I pass, I'm going to pass two iterators to both. But if I pass an input iterator tag, then I'm going to get the first function. But if I pass a random access iterator tag, I'm going to get the second. And because of the inheritance hierarchy, if I pass a forward iterator or something like that, that's going to see that as an input iterator. Okay, so how do we actually make the dispatch? Well, now we're going to go back and create yet another distance that actually only has two parameters, because that's what we want the caller to call. Because we're not going to ask the caller, when you call distance, by the way, you also have to pass in some tag nonsense. We don't need to do that. We just tell the caller, call a regular distance, pass in your two iterators, and what we're going to do internally is we're going to turn around, call distance, forward those 2 iterators, but our third parameter, though, we're actually going to get at the iterator trait for the get the iterator category of the iterator trait for the type of iterator that's passed in. So this is done at compile time. It's going to be inline. It's going to literally have no overhead cost at all. It's just as if we directly called the correct function. Does everybody see how that magic is done? And because this is done, as I said, at compile time, inline, doesn't actually cost us anything. That's the power of what we're being able to do by doing it at compile time. All right. Okay, so tag dispatch is one way of dispatching. There's another technique, and this is a compile time conditional overloading. So in this case, I want to talk about an example where we want to copy an array. We want to copy an array. We're given 2 arrays, the source and the destination, and they have to be arrays of the same type and the same size. And internally, we can just call stdcopy, right? But what's stdcopy going to do? It's going to go into a loop and copy the items one at a time, copying the assignment operator of these things, right? So that's going to work. It's going to be correct. But what if t was an int? Could we maybe do better than calling stdcopy if t is an int? We could do a memcopy, right? Okay, let's take a look at that. So what we can do is we can overload copy array for a case where we know that we have arrays of ints. Okay? Does everybody see how this is going to do the right thing in any case? But if we happen to have arrays of ints that are the same size, whatever size n is, as long as they're the same size, then it's going to do a faster, it's going to call memcopy instead. Does everybody see that? All right, that's great. But now, what if t were a float? Yeah, we've got a lot of types that we might have to write. And so what do we have? What does C++ give us if you have to do the same code for lots of different types? What do we do for that? We use a template. Right, okay, so let's create a template. So now we've templated this so that we can call memcopy for an array of any type. Now what's the problem with this? We've gone back to a redefinition, right? Because the original definition of copy array and this definition of copy array actually turn out to be the exact same signature. The implementation is different, but the signature is different. So the compiler won't know which function we want to call when we call it. So that's not going to work, right? What we really want to do is to basically say, well, if it's not memcopy safe, let's do stdcopy. But if it is memcopy safe, then let's do std memcopy. Does everybody see that? All right. So that's really what we're trying to say. That's what we have to figure out how to do it. And we could use tag dispatching here. We could make up a tag that would be one thing in one case, and we could do that. But we're going to use something different. We're going to use enable if. We're going to do this conditional overload and use enable if. And so the way this works is I'm specifying that the return value of these 2 functions is std enable if of a compile time constant and a type. Okay? So the compile time constant I'm using here is either not is trivially copyable or is trivially copyable, because trivially copyable is what the standard calls what I'm calling memcopy safe. If it's trivially copyable, it means you can memcopy it. That's what that means. And that is a property of types. And so we can ask that. That was one of the things in our, remember that big long list of type traits. Trivially copyable was one of them. So in this case, what enable if does is, if the compile time conditional is true, then the entire enable if just evaluates to the type that's being passed. In this case, void. And so what it's going to do is it's going to say in the first case that if what we're doing is not trivially copyable, then it's going to use the first function, which returns void. But if it is trivially copyable, it's going to enable the second function. And the return of that is, as I said, void. Now, one thing I'll tell you about enable if, there's actually a default value for the function, or excuse me, for the value. the second parameter. There's a default value, and that's actually void. So it turns out I didn't have to specify that at all. I just left it so you could see it. But this is actually one way I could specify this. Okay, so what's actually going on here is that we enable a function if this expression is true. A better name for this would actually be ignore unless. And the reason is that if you don't do anything at all, functions are always enabled. We don't actually have a step when we're writing code to say, okay, now it's time to enable this thing. If you write the function, it's enabled. That's what it is. So really, it's not about enabling something. It's about disabling something. That's what the actual trick is. That if this thing is false, we turn it off. That's what's really going on here. And so the name enable if, I think, is the wrong way around. It should really be called ignore unless, because that's what's really going on. If this thing is not true, then it gets ignored. Okay? All right. So the way this works is, if the expression evaluates to false, the function is disabled or ignored by Svenay. Svenay was invented by David van der Voort because he wanted a polite way to spit on people without having to say, excuse me. He just says, Svenay on you. No, that's not the reason. What does Svenay mean? Well, Svenay actually means substitution failure is not an error. And what this means is that as the compiler is looking for things that you might be wanting to call, so you write code that says copy array. So the compiler has to come up with what we call an overload set. The overload set are all the things that are called copy array that you might want to call. Now, there's a bunch of rules about what's in scope and all that kind of stuff. Let's just ignore that for now and just say there's a bunch of things called copy array. And so that's this overload set. This is a candidate set. The next thing the compiler has to do is it has to figure out which of them are viable. And so, in other words, if you pass only one parameter and there's a copy array that has two parameters, obviously it's not viable, right? It has to match. And then once it figures all the ones that are viable, then it has to see, well, which one's the closest? That's the steps. But when figuring out if it's viable, it has to figure out, in the case of a template, which is what this is, it has to say, well, what are the template parameters? If we're actually going to call this, what are the template parameters? And what it does then is it substitutes in with the actual parameters you're passing to see if it can figure out what the template type's deduced to be. And sometimes that won't work at all. If it won't work, then you have a substitution failure. And when you have a substitution failure, instead of just not compiling, it's not an error. It just ignores that particular template. If it tries a candidate in the overload set, if the candidate doesn't work for that particular template, there's no way to figure out what the template types are. Instead of failing to compile, it just says, well, I'm going to ignore this particular item. Now, of course, if that's the last viable candidate, then it's not going to compile at that point. But it will just drop anything where the substitution is a failure. So let's think about this for a second. How can we implement enable if? Well, the true case should be pretty straightforward, right? Because first of all, notice in the first one, I've done the primary template. I did that as an incomplete type. It's just a forward declaration saying there's going to be a declaration coming. And then I specialize it for the case where the Boolean is true. Does everybody see that? And if the Boolean is true, then my type is just going to be T. It's going to be whatever the type that got passed in, which if you don't pass it in is going to be void. But that's what it is. So if this evaluates to true, then we get the type. So that's pretty straightforward. But here's the tricky part. How do we implement false? What do we do for false? Nothing. Nothing. We do absolutely nothing. Why? I went too far. Oh, now we have to go back and re-implement it. OK. Why? Well, the whole point is that we don't have an implementation in the false case. So when the compiler tries to evaluate, well, what's the type in the false case? It's a substitution failure. And so that particular template just gets ignored or disabled, if you want to use the terminology here. OK? All right. So one of the things I want to say, that's kind of covered what I want to say about enable if, but I want to make one point, and that is the enable if can go on any type in the signature of the template function. So I put it on the return type. I think that was clear enough. However, it could be confusing to put it on the return type. You know, if you're reading it, it's the first thing you're reading. It may not be the most important thing about the function. Maybe you want to know what does the function do and then find out, oh, but it can be disabled, so it's got enable if in it. We can put the enable if on any type in the signature. We can put it on the return type, or we can put it on the type of any parameter. You can't put it in the body, so that's too late. It has to be in the signature, right? Because it's the signature that the compiler uses to figure out if the candidate should be called or not. So one very popular way of doing this is to add a parameter that you're never actually going to use. It has a default value. Notice in this example it says equals 0. So I'm creating a type that is enable if on my constant, and I'm giving it the type of int. Doesn't really matter what, because no one's ever going to call it. Right? It's only used to either disable or enable this particular function. And it is an optional parameter that's never actually used. But it is used by the compiler to figure out whether to turn this thing on or off. And that's kind of from a style point of view, that's the way people are going now, because that last parameter is just kind of ignorable, and it makes it more clear than what the return type is. Okay? Because you don't do anything fancy on the return type. That's just a style issue. It's going to work fine either way. Okay? All right. So now we're going to talk about, so up until now, what we've been talking about, the techniques have had the granularity of a function. By tag dispatch, we dispatched to a particular function, and the overloading was overloading by functions. So anything you wanted to do, you needed to create, you know, this function will be called or this function will not be called. But in C++ 17, there's something new in the standard, which the standard calls const expr if, but is actually spelled if const expr. Now the thing about the standards committee is they're really helpful, and they want to make certain that we won't be confused about whether it's const expr if or if const expr, so they give it a very clear name that is the exact opposite of how it's spelled. That is, you know, your committee working to support you. Anyway, so it's called if const expr. And what this does is it allows us to do conditional compilation things within the scope of a function. Everything we've done up till now, as I said, was the granularity of a function. Either we use this function or we use this function. We either use tag dispatch or we use enable if or spna to figure out which function, but it's an entire function. But now we can actually do something like this, where within our function we have a single function called copy array, and it says if const expr, and then of course we have to give it a compile time constant Boolean expression. Obviously, if it's runtime, we can't figure it out at compile time, right? So if we say if const expr, the expression that we give it has to be evaluatable at compile time, which, what is this? This is trivially copyable as a type trait, so we can evaluate that at compile time. So if this is true, we're going to go down the first branch. Otherwise, we're going down the else branch. Okay? Does everybody see how this is being done now? Right? Compiler will evaluate this at compile time. And at compile time, it's either going to generate the code that calls memcopy or it's going to generate the code that calls stdcopy. And the branch that's not taken is termed in the standard discarded. Right? Those statements are discarded. And what that means is that they syntactically have to be parsable by the compiler. Notice here, the compiler, as it's scanning that memcopy, it needs to know where the end of the branch is and where the else begins. If you just started typing random things, the compiler might not be able to parse it. So syntactically, it has to make sense. However, for the discarded statement, it doesn't have to make semantic sense. It's possible that the type doesn't have the member you're referring to, or it's possible there's no function that has that accepts the types you're trying to pass to it. If it's a discarded type, the compiler doesn't care, because it doesn't actually have to generate code. It has to understand it. It has to be able to say, oh, this is a function call, fine. And this is a semicolon. It's the end of a statement, fine. Now I'm looking for the right brace, right? It has to be able to parse it, but it doesn't have to be able to make code out of it, because it's not going to, because it's discarded, because at compile time it goes away. Okay? All right. So I think that this approach is going to be way more popular than the approach that's at the function granularity. Why? Well, fewer functions, less duplication. Right? If you're duplicating the function, you may not duplicate much, but you're at least duplicating the name of the function. You know, there's some duplication going on. And what does that mean? That means it's harder to read and comprehend. It's easier to read one function that has, you know, a compile time if in the middle than to say, okay, I have this function and I have this. Maybe there's a third option here somewhere too. I don't know. And then that makes it also easier to maintain. I'm maintaining one function that has a conditional compile time conditional in the middle, but it's one function that needs to be maintained. Okay? So I think this is a great addition to the language that we're seeing in C++ 17. All right. So the next thing I want to talk about are policy classes. So policy classes were made popular. He may have even invented them, I don't know. But Andrei Alexandrescu wrote a book called Modern C++ Design, and he popularized policy classes because he used those. And by the way, this is a great book. You're going to enjoy this book. All right. Okay, so what's the idea with a policy class? So when we design a type, any type, as we design it, we're answering a bunch of questions. That's what we do. We make design decisions. Are we going to do this? We're going to do this. We're going to do this, do this. In some cases, depending on what we're working on, the answer is really clear. Suppose that the type we're working on, the whole point of it is to take up as little memory as possible. We're optimizing for small memory. Well, as we go through and we ask a question, well, which way should we do it? Well, this is the way that has the least memory footprint. That's the decision we're going to make. Now, sometimes, as we're working on a library, we get to a point where we say, not quite clear here what is best. And some users in some use cases might want this option, but some users in other cases might want this option. So how do we deal with that? Well, on our function, we put a parameter that says whether we do this one or this one. That's great if it's runtime. But sometimes we'd like to be able to make decisions that really only make sense at compile time. So for example, there might be one path we'd go down where we'd want to have some extra data members. We can't add extra data members at runtime. That is a compile time decision. Now, we could always have the extra data members, but that's completely wasted if we don't need them. So sometimes we can make runtime decisions in our libraries, but sometimes we want to make compile time decisions. And again, it's the library author doesn't want to make this decision. The library author wants the user of the library to be able to specify, this is the behavior I want to give. Now, understand when I'm talking about this, the library author gets to decide what decisions can be deferred. In other words, the user isn't rewriting the whole library. It's not that. It's that the library author said, when we get to this point, you can decide what we're doing at this point. So the library author decides where the customizations, what possible customizations there are. It's also possible, and it's very common in fact, for the library author to come up with some obvious implementations. So let's take a look at this. What we have is I'm creating a container, and the container has indexing. And one of the things I want to allow users to decide is, how do I check to see if my index is in bounds? Okay? So I have a container, and I want to have a checking policy. And the way this is implemented is, this is a templated parameter that I'm going to derive from. So what that means is, if this checking policy class has a member function, I can just call it, because it's going to be in my base class. Okay? So what is my checking policy function going to look like? Well, it basically has to have a member that says check bounds. I'm going to pass in the lower bound, the upper bound. I'm going to pass in the actual index, so that the checking policy can check to see if it's in bounds or not. Okay? All right. So what are possible things I might do? What does vector do in this situation? So nothing is a really viable thing. In fact, it might be a very popular choice. The do nothing to do checking. There's no checking being done. It means that the caller has to do the checking beforehand. What else might I do? I could throw. Okay. What else might I do? I haven't really architected this so that you could return a default, but that would be maybe another version we could do. There's other things we could do. We could just log it. We could assert. We could drop in the debugger. There's a bunch of things that a user might do. But the author of the class could create some reasonable policy. So the author of the class might create the do nothing policy or the assert policy or the throw policy, right? And what's happened now is that the author ships a library, and if what you want is the do nothing, then you just say, I want to, here's my container, and I'm going to use the do nothing policy as my policy class. Or you could do one of these others, or you could write your own. That's the beauty of this, that you are completely able to put in whatever checking policy you want by just writing it, and it derives from that. Okay? Now, the question is, why not just use a virtual function? Right? Why not just make our container a base class that calls a virtual function that says do the check? And then you could derive from it, and you could implement the virtual function to do whatever checking you wanted. Would that work? Could you make a correct class that way? Yes. You could have it just return to do nothing, or you could check and throw an exception, or you could log, or you do all those things, right? Why not do that? Why, and then we don't have all this fancy compile time stuff going on. Why not do that? What's the overtime? Yes. The overhead, if we did this with a virtual function, there's a couple of issues. One is calling the virtual function itself requires an extra dereference, right? Because it's a virtual function. We've got to go to the V table to figure out what that is. But what else is going on? The other thing that's going on is that virtual functions, as a general rule, cannot be inlined away. So even in the do nothing case, you're going to do a dereference to get to the function. You're going to call the function only to find out there's nothing there, and you're going to return. And the reason we want to do nothing is because we want the performance of not doing anything. We can't make that go away. So that's why the policy class wins out, from a performance point of view, certainly wins out over virtual functions and an object-oriented programming approach to this, because in a compile time situation, the compiler can inline solutions, and in some situations, that's not just a small win, but a huge win. Okay? Yeah?
Absolutely.
What about it?
Well, if you use a virtual function, it's not type safe.
If you use a virtual function, it's not type safe.
Use a base class for a virtual function.
Yeah?
If you're still calling the virtual function from the base class, and you're forwarding the call to another policy class. But you're not really knowing which option or which function you're calling. But if you use a template function, then you're having two different types. Because you're using two different derived classes. You're using an implementation with a different template type.
I'm not sure I'm following you.
You're using two different policy classes in two different in the same implementation.
Okay, so I think my model for the virtual function solution would be that we wouldn't have a policy class, we just have a base class.
Yes.
The base class calls a virtual function. And then the user decides what kind of policy they want by deriving from the base class. So they have a derived class that they're actually working with. And so the derived class code, most of it is this base class container. When it calls the virtual function, it gets dereferenced to the derived class and implements the checking policy in the derived class.
So you're not finding the policy at the compile time?
No, that's what I was comparing against. The type for the policy class that I was saying is all bound at compile time. But what I was saying is that I think has a performance win over the virtual situation. And if there's a difference in safety, I don't see what that is.
Some of the safety difference is calling the virtual function in the destructors is a dangerous thing.
Okay, so I don't know what your name is, but Richard pointed out that calling the virtual function in a destructor would be a dangerous thing to do. That's absolutely true. And if there was a possibility that you needed to do that, then there is kind of an issue where even more you'd want to use a policy class, because a policy class can be more flexible in that way. There's that. Yes. All right. So let's take a look now at perfect forwarding. So perfect forwarding, again, is not a beginning template thing, but we're learn a little bit about templates, and we're going to jump into this. So perfect forwarding comes in when we have a situation where we are looking at essentially layers of code. And so there's an upper layer that's calling down into a lower layer, and we're responsible for writing a layer in between that's going to do something interesting. But what we want to do is the data, the arguments passed into us, we want to simply forward them down to a lower level and do nothing with them. We're just forwarding them on down. So here's an example. Suppose I have written an application, and my application depends a lot on a particular library that I'm using. Maybe it's a graphics library, maybe it's a networking library, but it does something. I spend a lot of time in that library. And the question comes up, how much time do I spend in that library? That's what I want to do. What I want to do is I want to measure, instrument every call into the library and know how much of my time I spend in the library. So one thing I could do is I could create a little helper class that helps me do this. And what this is it's going to time a call. So you pass in a function, and it's going to call that function. But before it calls the function, it's going to put this API timer object on the stack. And the API timer object, all it does is it calls now in the constructor, calls now in the destructor, figures out how long that object has existed, and every time the destructor is called, it calculates how long it is, and it adds that to some static data member that is keeping a total elapsed time. Does everybody see what this API timer is doing for me now? I just put it on the stack, call the function, and then when the function returns, it gets popped off the stack, it goes out of scope, and that tells me the elapsed time that I spent inside that function. Does everybody see how this solves my problem? And fortunately, all the libraries I've ever worked with didn't have any parameters. So it made it really simple. No, that's a problem, isn't it? The problem is that it's really simple as long as I have a function that I don't have to pass any parameters to. But let's think about this. Suppose there was a parameter that I'm going to pass here. So, I was going to make the point that I don't have to say what the return type is. If I was doing this in C++11, I would have to say that the return type is the decal type of whatever I get when I call f. Okay. So the function has a parameter, and so all I need to do is take initial template parameter for capturing the type and the value of the parameter that's passed to my time call function, so I can turn around and pass it to f. See how this is simple? But there's a problem here, right? Suppose what f is going to do is it's going to modify t. It takes it by reference and modifies it. Would that work? Would this compile? Yes, it's going to compile, right? Is it going to modify t? Well, it's going to modify my copy of t, but it's not going to modify the original t. So I've broken the code. So what do I have to do? Well, okay, so I can take it by reference. Okay? All right. Does that solve that problem? And the way I ask that, it's clear there's another problem coming. What's the other problem coming? What would be the problem with using this? Right. If I passed a temporary, which I could in my code, it could be that when I call f, I pass it in a temporary, the result of some expression. And when I do that, that won't bind to an L value that's not const. An L value reference that is not const won't bind to a temporary. How many of you gotten that error before? Right? Can't bind a temporary to an L value reference. So we can't do that. So we could do this. If it is a temporary, then it's an L value const. But if it's not, if we want to modify it, we have to do, this could get pretty ugly as far as having to make a bunch of overloads for every possible case. On top of which, what would happen if we had more than one function? Okay, so let's deal, first of all, let's deal with the situation of being able to capture any type. And the solution is something called a forwarding reference. Now, Scott Myers called this a universal reference. How many of you have read Scott Myers' book on, wow, no wonder you guys have such a great user group. All right, so you guys have read Scott Myers' books, and he refers to this universal reference. And why is it a universal reference? It's because this reference will bind to anything. It will bind to L values, R values, volatile, const, you name it, it binds to it. So it calls a universal reference. When Scott made this name up, he actually got a lot of heat from the standards committee. I was actually on a thread with Scott and Herb. I was CC'd, so I got to watch the thread going back and forth. And Herb was saying, wait a minute, the committee created, in C++11, we created one new reference type, an R value reference. But you're making it sound like we did too. You're making it sound like we've made it more complicated than we really made it. And Scott replied and said, look, your R value reference, you're telling people that you can move from it. But sometimes you can't move from it. So your message is that R value references are things you can move from except when you can't. And that is hard for people to understand. So I've made up a term for the situation when you can't move from it. That's called a universal reference. If it's a universal reference, it may be an R value reference, it may be an L value reference, and I'm trying to make it easy to understand, even though technically it's always an R value reference. So Herb pushed back and said, you're confusing the issue. And Scott pushed back and said, no, I'm clarifying the issue. So the standards committee did not like universal reference. They refused to use it. However, the next version of the standard, they had to be able to explain in certain situations why you wanted to have, and so the standards committee made up the term forwarding reference. So I think they pretty much admitted that Scott was right, that they did need a term, because they invented that term. They didn't want to use universal reference because, well, you know, not invented here. Okay? I used to work for a company that had their own term for not invented here. All right, so it's late. It's late. Give me a break. All right. So the point is we have this thing called a forwarding reference, and a forwarding reference can bind to an L value or it binds to everything. Now, when we bind to it, though, we have to be able to distinguish in some way, well, is it an R value or an L value, because we want to behave differently. Why? Because remember, the point is we're moving data from one layer to another layer. That's what the forwarding is doing. So we want to forward it by calling a move operation if it is a temporary, but we want to call it with a copy operation if it's not a temporary, if it's an L value. Okay? And how do we do that? We do that with something called std forward. And what std forward does is, std forward is templated on T, where this uppercase T that it's templated on is the same T that we got it in as. So it's passed in as a forwarding reference or a universal reference, and whatever the type that comes in as, we forward it as that. And what this allows us to do is we don't have to write two different paths. We don't have to say, oh, this came in as an R value, so I'm calling the move path. This came in as an L value, so I call the copy. No, I do a single path. A single path. I just, in this case, I'm calling F, and I'm forwarding. And what the forward magic does is the forward forwards it either as an L value or an R value, depending on what was passed into us. And that allows the compiler to pick the version of F that wants to take moves or the version of F that wants to take copies. Right? So that's what forward's doing. It's doing a conditional, either a move or a copy. Okay? All right. Now, what if there's more than one parameter? Well, it might sound like, uh-oh, now we got a problem. It turns out that's not such a big deal. We're going to use variadic template parameters, which was introduced in C++11. So this is something that causes problems for instructors, because all over our slides, when we want to say, oh, there's some other code here, we put ... Now suddenly ... is actually part of the language. Whose idea was that? Okay. So let's take a look at what we're actually doing here. So generally speaking, in our template block, we say either class or type name. We say class, and then we give a name of a template. But we can also say now class ... And what that's telling us is that the args in this case is not a template parameter, but a pack of template parameters. It's some arbitrary number of template parameters, 0 or more. It might be 0. Right? That's what the class ... is telling us, that args is actually not a type, but a 0 or more independent types. They might all be ints, but they might be different types. All right, then in the function signature, we reverse it, and we write args, capital Args, followed by 3 dots. And that's unpacking the template pack to create a parameter pack. So lowercase args is not necessarily just one parameter. What it is it's a pack of parameters, 0 or more parameters whose types are defined by the pack in args. And the way it does the unpack is a smart way of doing it, because the compiler knows that we aren't trying to unpack args. We're trying to unpack args ref. In other words, we're making R value references to all of these, except they're not really R value. What are they? They're forwarding references or universal references, right? Okay, then inside the body, we're doing yet another reverse. And this time we take lowercase args and put ... after that. And what that does is it tells the compiler to unpack the parameters that we got passed in and basically put a comma between them. But again, it's doing it in a smart way, so it's doing a forward on each individual parameter. Okay? So the problem of doing multiple parameters actually turns out to be pretty straightforward. Again, this is something that is fairly straightforward to us now. We use forwarding parameters and variadic parameters, and that gives us what we call perfect forwarding. This was possible in classic C++, but it was really hard. The Boost library authors figured out how to do it. They didn't have variadic template parameters, but they were able to write libraries where you could pass in an arbitrary number of parameters up to infinity, where infinity is defined to be 12, right? But now we can use the compiler and the compiler feature to clean that up a lot. So it was, impossibly hard to do before, but possible, right? Now it's pretty straightforward if we combine these two features. Yes?
Actually, I run into this, I did some metaprogramming, and there was the same thing, but it ended up in an infinite loop of the template instantiation, and the compiler has an infinity limit. With Cloud, it was around 100,000. And it
Wow.
took 30 gigabytes of memory to stop there.
Delightful. Cool. All right. I believe in the original 1998 standard, the number of levels that a template can possibly go down is not defined in the standard, but I believe there's a recommendation of what an implementation should do. And I believe in the standard it was like 17 levels down. By today's standard, that would be nothing at all. We couldn't do any of the cool template stuff that we do. But the original one was 17 levels down. And the reason was that by the time you got to 17 levels down, it was time to go eat anyway. I mean, it was just really, really slow. Our compilers are much, much faster now. All right. So here's kind of what our answer would look like. And here we have an arbitrary number of arguments passed in and forwarded on, so that so this is a solution to my problem. All I have to do now is go into my code base and change every function call and wrap it in time call and pass in the function that I'm calling and all its arguments. And then when my application is finished, I can look at the API timer's static accumulation of all the time passed. That's how I can solve that problem.
So what was the return time stand forward? Or does it unpack the result of stand forward?
Okay, so the way this works is we're unpacking the lowercase args with the ... because the ... is right of the lowercase args, right? And the way it unpacks it, it looks at the expression that args is part of and duplicates or unpacks that entire expression repeatedly. So what we actually have here is std forward of args, the 0th argument, the first argument in the parameter plaque, std forward of the template type of that, and in parentheses, the actual parameter value that corresponds to that, and then a comma, and then repeating that. So it's standard forward of the second parameter's type, cast or provide, wrapped around of, I should say, the second of the args. Does that make sense?
So in theory, would it be possible to make a larger expression there and call that? I mean, could you kind of compose a larger expression which is not only sit forward, but has something around the sit forward, and then do the...
Yes. This expression with args in it can be arbitrarily complicated. Absolutely. That's what it's doing. This isn't, this expansion isn't like a macro kind of thing where it's these characters. No. The compiler understands this expression and will update the expression. In fact, if you look at this, it's actually unpacking the template args along with the parameter args, right? It has to keep those in sync as it's doing it. And it's smart enough to do that. Okay. All right. Perfect forwarding is not really perfect. There are some failure cases, but it is a really valuable tool for us in writing templates. All right, so the last thing I want to show you is not actually something that you will ship in your code, but it might be a valuable tool for you as you're writing code, as you're starting to do template things. So as we do template things, we're relying on the compiler to deduce template types all over the place. And sometimes we might get into a situation where something's not compiling. I know you guys have never seen that, but I've on occasion had situations where something doesn't compile. And the reason it doesn't compile is right there. It's telling me, you can't do this thing with that type. I'm saying, but that type is this. It should be able to do that. Why? The compiler isn't deducing the same thing that I'm deducing. I'm probably right, of course, but try telling the compiler that. All right, so the problem we have is we would like to be able to look at a type that is being deduced by the compiler and have the compiler tell us somehow know what that type is. So one way of doing this is, any of you that are using modern IDEs, you can probably hover your mouse over it, right? Or if you use something like CPP Inside or a tool like that, you can probably use something like that. But some of us, our idea of an IDE is Vim, right? So what do we do if we don't have a sophisticated IDE? All right, so we're going to look at three options. One is using the standard, the other is using Boost, and then we're actually going to ask the compiler directly. So if you include type info, the header type info, you can actually get a type ID of any type and then call .name on that, and that will give you something that might be helpful. Why do I say might? Well, first of all, the standard specifically says that it's going to drop const, volatile, and reference. So it's very likely that that's the part that you're confused about. It's like, well, is it deducing it as const or is it deducing it as, I don't know, right? But if you don't need const, volatile, or ref, then this will tell you. But then you have to unmangle the name because the name might be PK6 widget. So you know what PK6 widget is? It's mangled. What is it? Pointer to a const widget, right? Pointer to a const widget. Of course it is. What else could it possibly be? All right. So this is not terribly helpful. A better solution is provided by Boost. If you include the Boost header, there's a call called type ID with CVR. What do you suppose the CVR is? Well, of course, the CVR is const, volatile, and reference. They don't throw that away, and so they tell you because that's something you might want to know. The other thing is they don't call it name, they call it pretty name. And what does that mean? That means they unmangle it for you. Instead of saying, PK6 widget, it will actually say this is a pointer to a const widget. And that means, of course, that it's implemented differently for every compiler because every compiler has its own way of potentially its own way of name mangling. So the Boost library has to figure out for whatever compiler you're running, how does it name mangle so it can undo this. So I think the Boost approach is much better than the standard approach for those two reasons. One is it includes const vol and a ref. The other is that it unnamings. But both approaches have one really fundamental problem, which is what? This is runtime. It means that it's got to compile and run. And if the reason that you want to know the type is because you can't get it to compile, it's not as helpful as you might expect. So this is an idea from Scott's book, and those of you who read Scott's book have already seen this. He does it a little differently, but the idea is the same as what Scott does. So we've created this type, this primary template type called that type, which is a forward declaration. We don't actually say what that is. And then we create this function called name that type, and internally name that type. What it does is it creates a that type of the t parameter, and then it creates a that type of the decl type of the param. So it's telling us then what the type is and what the param type is. Why? Because when we try to compile this, it's going to fail to compile. Why is it going to fail to compile? Because this function is going to try to instantiate that type on t and the decl type of param, and it can't. Why? Because that type doesn't have a definition. So it's never going to compile. You put this code in your program, it'll never compile. That's my personal guarantee. But why do you do it then? The reason is, look at the error message. Now, every compiler is going to have its own flavor of what the error message is, but they're all going to have one thing in common, which is they're going to tell you that the problem is that type of char, or that type of widget, or that type of, it's going to tell you what the T is. And you don't need to be able to compile it. So if you have a great IDE, a modern IDE, that's great, but if you don't have a modern IDE, you can use this technique to get the compiler in its error message to tell you what type it thinks you're working with. Okay. All right, so that's pretty much what I wanted to talk about. Do we need to do anything else before we break up? What are we doing, Klaus? Questions? Questions? Thank you very much. Thank you. All right, we have a question.
What would be a good way to debug compile time functions?
What would be a good way to what? Sorry?
Debug compile time functions.
So what he asked was, what's a good way to debug compile time functions? Probably the best thing is to just not make any bugs in your compile time functions. Yeah, so that's tough. That's tough because of what you're looking at, right? If you've ever used the Boost HANA library, it's actually been designed specifically so that you can, anything that you could do at compile time, you can also do at runtime, and it makes debugging really nice. I don't know that there's any special general magic. Anybody else have an answer to this? I don't know that there's, I mean, you just work, yes?
I believe, I'm not sure about this, but I think Clang has a static print, so you can print something at compile time.
Okay, so Clang has, what did you call it?
Static print, I'm not sure about the name.
Static print.
Yeah, it's
Okay.
an extension of Clang.
Okay, all right. So if you're using Clang, static print will give you compile time information. Okay? All right. All right, other questions? Yes, there's your hand.
Yeah.
Oh.
About CRTP. You mentioned the potential solution to inheriting from the wrong derived type was to put as a friend. But I wanted to ask, like, is that really the best solution? Like, if your base class is complex and has members of its own, like in the case of the counter, then being a friend will mean that the derived type has access to all of its parents' internal types, which I feel like would be rife with bugs for people that are like trying to use this CRTP. So they accidentally have access to all of the internals that they wouldn't normally have.
That is true. If you really are paranoid about that, you can create a two-level, right? So in other words, you have a class that has all the data members, and then another class that you would have as a friend and have the private constructor. Does that make sense?
Yeah.
Right? I mean, I personally probably wouldn't go that far. What I would just say is, if you're messing with the privates in the lower class, you get what you get, right? But you could do that. You could have a base class that actually has all the data that you want to protect as a separate class, and then derive from that, and have that class have a friend of what the derived type is. I think that would work for you. I haven't ever tried it, but I think that would work. Okay? I think you had a question, and then back there.
In your perfect forwarding example, the return from the template is what the declare type also. I didn't understand why not simply auto.
Oh.
Yeah, right? We could just go ahead and say auto.
Okay, which one was this? This was perfect forwarding. Okay. This one here. So probably, although, okay, so the reason we do this is because there is the possibility that what f returns is actually a reference. If f returned a reference and we just said auto, that will never be a reference. It would drop the reference, right? So if what f is returning is a reference to widget, then the auto of that would just be widget. But the decal type auto of that would be reference to widget. That's why I didn't stop and explain that. I'm sorry, go ahead. Oh, because I don't think I did that for ... Is this what you're talking about? It's still possible that this API function could return a reference. And if it did, I'd want to return that reference. I want to pass that reference on through. So I believe the decal type auto option is introduced in 14. I don't think you can do that in 11. That's a 14 feature. Okay? And it's, I mean, there's not often that we have standalone functions that return. Member functions, assignments often return references, but having a standalone function return a reference, probably not a great design idea, right? Because that reference, who knows what its lifetime is, blah, blah, blah. But if you did return a reference, that's what, I mean, I don't want to get in the way of that. So I'm just going to pass that reference on through. So that's why I'm doing decal type of auto. Yeah. Oh, I'm sorry. Wait a minute. I think the question back here in the blue shirt. Yeah.
So about the CRTP case, whether a static assert is base work or is it not possible to cross the incomplete typo?
Exactly what?
Oh, to prevent the derive class?
Yes.
Yeah, I think you could probably do that.
And it would be way much more expressive because you actually, with this magic, with the friend and the private constructor,
That's probably a better approach. Yeah, it's probably a better approach.
what you want. But if you write if context is base of blah 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 static assert, you are not my base.
Yeah.
Then it will be, everybody could read it even without knowing what it is.
Right. So the question is, would a static assert be a better approach than what I showed in the slide? And the answer is probably, because both of them would have the desired effect of preventing the typo that we saw. But the static assert would be more expressive. Right. Klaus, did you?
It would be more expressive. You would put it in a base class, right? Doesn't work because the derived class does not exist at the point the base class is instantiated. You cannot ask the derived class anything in the base class.
But it is base of, it's a compile time.
It doesn't exist the derived class. You cannot ask it.
Will you put it in a function of the base class?
No, I think that's right. I think you're going to be stuck with All right, we got some questions going now, don't we? All right, you have a question over here?
Yeah, it's just that you said that it's not common to return a reference from a normal function, but here you could also put in some kind of closure or some kind of makes sense to return a reference, right?
So I think what you said was that we might have a function that returns a closure.
No, I mean, instead of API, as an API function, you will pass in an instance of some functor, right, of some object, and then it may make sense to return a reference because that object can hold a reference to some other thing somewhere.
Okay, so this API function, that f could actually be a closure,
Yes.
right? Which would work here. I'm not sure why that has anything to do with the return type.
Because there it makes more sense that you would return a reference, right? Because that object would have an internal reference member.
I'm not sure that it makes more sense. It's certainly possible. Yeah, it's possible. Sure. Okay. All right, over down here.
Is there a way to bind to a callable that you don't care about what the parameters are? You just want to templatize to a callable?
Is there a way to bind to the callable?
Yeah, you have a template parameter that you don't care if it's a function, if it's a lambda, if it's some callable class. You just want to check if it's callable.
You want to check if it's callable.
Yeah, a static check. At compile time, you want to guarantee that your template is callable.
There's a type check for that.
But you have to specify the parameters.
So there's a check that is going on here. If this f is not callable, it will not compile. I mean, I'm not sure what you're trying to guard against. So the question I should say, the question was, is there a way to verify that f in this template we're using here, that the f that's passed in is callable? And I'm not sure what you're trying to guard against, because if it's not callable, it just isn't going to compile here.
So in my case, I was trying to do a class that stores a pointer to the template. So I only know if I can call it or not at the call site, but not at the construction site.
I see. I see. So what you can do is you can do a decal type to find out what the type would be if you did call it. And if it's not callable, then it's not going to compile.
But you can only do that if you know the parameters. And at construction time, I don't know the parameters. Only at
Oh, I
call
see.
site.
I see. I see. So you're capturing something that is theoretically callable with some arbitrary parameters you're going to get at some point later.
Yeah.
This is what std function does.
Oh, that's true. You could no, but you couldn't put it in std function because std function has to know the signature too. I was going to say, yeah, you could store that. In fact, that's what I would.
What's the problem with learning this at the call site? Because that's when you're trying to call it with the argument that you already know, and then you will learn if it compiles or not, if the type is wrong.
It's not a big issue, but it's a little unclear because you are able to build the class, and you don't want to be able to build it because you know it's wrong, because you cannot call it.
You know, I think it's kind of irrelevant to know if something's callable in the general sense. Because since you don't know what the parameters are passed to you, I mean, suppose you found out, oh, yes, it's callable with some set of parameters, but it's not the ones you're going to get eventually anyway.
But if you get, for example, a functor, you may have a set of overloads, and you can have different kinds of parameters that you can pass in the future. And at some point, you may get an error or not.
Yeah, but what I'm saying is, if you knew this object is callable, that with some set of parameters, that doesn't really tell you anything. Because what you want to know is it going to be callable with the parameters you will be given, which you can't possibly know. So I'm not sure. I mean, I can understand why you're asking. You say, oh, is this something I could call? Yeah, that kind of makes sense, but it doesn't really make sense because it doesn't really tell you something you could act on.
So let's have one more question.
All right, one more question. Or I think the pressure to get a good closing question is too great, Klaus, and we're gonna have to let it go. So I'm gonna thank you. Wait! Somebody steps in. That's probably a good closing question, isn't it? What are we going to do with the video here?
Yeah, the video should be on the YouTube channel, and if you send us the slides, we can make them available on the meetup page.
I can send you the slides, or you can go to Meeting C++, where I just sent them the slides, and it's the same set of slides as what I just did there. Or you can pull them down from there and move them over. All right? All right. I want to thank you guys. You've been great. You've been a great audience. You guys have a great meetup going on here. Thank you very much.